Hello everyone, let's talk about our project, MimicTouch, leveraging multimodal human tactile demonstrations for contact-rich manipulation. Insertion test is an important test in the industry. Current learning-based methods mainly rely on visual feedback. However, visual feedback required good whitening conditions. For example, in the car assembly test, it has poor whitening conditions. Under this scenario, both human and robot only can use their tactile feedback to get the contact information and finish the task. The second thing we want to highlight is why we use human play data. According to this video, we can see that human play data is much faster than the teleoperation data. Also, it has much more diverse motion, and the most important thing is that humans can utilize their human tactile feedback to get contact dynamics information during the data collection, whereas the teleoperation system, human only can use their visual feedback to get the contact information, which has gap between the human visual feedback and the collected tactile data. To bridge this gap, we introduced the human tactile demonstration data collection system. We use it to collect the proprioception, the tactile images, and audio signals. We will use the innovator learning framework to learn the human tactile control strategy. Then, we choose the non-parametric nearest neighbor imitation learning. We want to reduce the components error getting from the human demonstrations and deploy it to the real robot. To bridge the embodiment gap between human and robot, we use the online reinforcement learning to refine the policy and deploy it to the real robot. Then, we want to evaluate our human tactile data collection system. We find that the human tactile demonstration is much faster than the teleoperation system. Also, it has much higher success rate to collect usable demonstration than the teleoperation system. Here is a demo. According to this demo, we can see that the teleoperation data has a lot of useless motions and contact informations. Then, we want to evaluate the offline policy learned from the human tactile demonstrations. We compare our non-parametric nearest neighbor-based imitation learning algorithm with the SOTA parametric imitation algorithm MUSA, which also be used in multisensory imitation learning. We find that the VRNN-based method has much lower MSE loss than the MUSA. Then, we also want to compare the human demonstration policy with the teleoperation policy. We visualize the action serial numbers, and we see that it almost has linear relationship in the human demonstration policy. However, in the insertion phase for the teleoperation policy, it has great variance. Here is a demo for human policy and the teleoperation policy. Human policy can reach 40% success rate, whereas the teleoperation policy only has 12% success rate. Then, we conduct reinforcement learning to refine our policy. After 3 hours training, our policy can reach 96% success rate. At 2 hours, our policy can reach 88% success rate, whereas the teleoperation policy only has 32% success rate. Here is a demo for the reinforcement learning training process. It has 3 iterations in this demo. Then, we conduct zero-shot generalization experiments in 5 different test domains. The first one is the shifting experiment. We shift it for 0.8 cm. The second one is the tilting experiment. The third one is the two-stage packing. The fourth one is the multi-material dense packing. It has paint, sponge, and tissue in the box. Lastly, we conduct furniture assembly task. We compare our policy with the open loop policy. We collect 5 different trajectories from the initial setting and test it in the 5 generalization test domain. And we find that all the tests are pretty challenging. With those challenging tests, our MimicTouch framework still has very nice performance. Here is the demo for the shifting test domain. We shift it in 4 different directions. It's a demo for the tilting text domain. It has 10 degrees and 20 degrees. Then is the dense packing. For the dense packing test, we can show that our policy can adjust the pose of the objects according to continuous contact information and make continuous changing in the real time. Finally is the furniture assembly test. Notably, the finally rotation is a manuscript. We want to use it to test our policy can insert and adjust into a correct pose, which means that the object can be screwing into the table or not. Finally is the ablation study. We want to show that both the tactile and audio feedback play as great contributions in our framework, and it has lower MSE loss and higher success rate than single modalities. Then, we also visualize the contributions of each modality during the task. In the reach phase, the state played the major contributions, whereas it's no contact. During the insertion phase, all of them play major contributions because there are a lot of contact between the objects and the whole. Here is the demo without tactile feedback and audio feedback. Without tactile feedback, it's hard for the policy to find the correct directions. Without audio feedback, sometimes tactile feedback cannot get the contact informations and it cannot make the correct actions. Thank you for watching our video.